So here we go. So welcome to section 8.1, chapter 8, section 8.1. In chapter 8, we're going to take a look at what we did in chapter 7. That is, we're going to take a look at probability a little more. But what's going to happen in chapter 8 is our sample spaces and our events are going to get bigger. And because they're going to get bigger, it's going to be harder to count how many things are in the sample space or in the event. And we're going to need some new math, some new techniques, some new approaches to how we go about doing that, how we count up how many things are in our sample spaces and our events. So we're going to start with chapter 8, section 1, take a look at something called the multiplication principle, as well as permutation. So we have three objectives here to take a look at the multiplication principle, permutation, and distinguishable permutations, which are different. We're going to start with the multiplication principle. All right, so take a look at an example to begin with, and we'll build from there. Suppose that you have a choice to make breakfast. And for breakfast, you can choose one pastry, and it can either be a bagel or a muffin or a donut, and one beverage, and you can get coffee or juice. So how many different breakfast options are there? Well, if I think about what's going on here, I could actually kind of write this one out. I could say I could have a bagel and coffee, or I could have a bagel and juice, or I could have a muffin with coffee, or I could have a muffin with juice, or I could have, what else could I have? I could have a donut and coffee, or I could have a donut and juice. So it looks like I have 1, 2, 3, 4, 5, 6 different ways that I can make breakfast, or that I can have breakfast, given these options right here. Now I also could have made a tree diagram. I could have my bagel, or my muffin, or my donut, and then I could have coffee or juice, or coffee or juice, or coffee or juice. And I could have listed it that way, and I could see that there are 1, 2, 3, 4, 5, 6 different paths through this tree diagram. So there's 6 different ways to make my breakfast. And for a situation like this, an example like this, this is pretty straightforward. This isn't too bad. This would be a decent way to have it. But what if instead of 3 options, there were 12? And what if instead of 2 options, there were 5? Well, I definitely wouldn't want to list them all then. And I'm absolutely not going to draw the tree diagram for that. So I need something bigger, some more powerful mathematics that is going to help me count things more quickly. And that's where the multiplication principle comes in. The multiplication principle says that if you can take a big event and break it down into steps or choices along the way, and at each step or choice, the number of ways that you can do it are known, so that like on step M1, there are M1 ways to make choice 1, and there are M2 ways to make choice 2, and there are M3 ways to make choice 3, and so on and so forth. Then if I just multiply together all those M's, M1 times M2 times M3 and so on, then what that will give me is it'll give me the total number of ways to make the entire sequence of choices. For example, if we say that choice 1 was our pastry, then M1 would have been 3. And if we say that choice 2 was our drink, then M2 would have been 2. And then the multiplication principle says that M1 times M2 is going to be the total number of choices here, we would have 3 times 2. Oh, oops, I got ahead of myself there. I've given away the answers. We get 3 times 2, which would give us 6, and that will be our total number of choices. Again, for an example this small, that wouldn't be too bad. But what about my hypothetical example? Well, M1 would be 12 because there were 12 pastries, and M2 would be 5 because there were 5 drinks, and then 12 times 5 is 60. So there'd be 60 different breakfasts. Multiplication principle. You break it down into steps. As many steps as there are. Okay? If you can break it down into 5 steps, then you have 5 M's. If you can break it down into 10 steps, then you have 10 M's. It really doesn't matter how many steps. Break it down into steps, multiply all the steps together, gives you how many you got. So for example, here we go. Ready? A menu offers a choice of 3 salads, 8 entrees, and 7 desserts. How many different meals are possible if one of each is chosen? So in terms of the language of the counting principle, or the multiplication principle, sorry, that would be our M1 number of choices. That would be our M2. That would be our M3. And then we would say that there are 3 times 8 times 7. Okay. And what's 3 times 8 times 7? Let's see. 8 times 7 is 56, so that's going to give me 3 times 56. That's 168. So there are 168 different choices, different meals. Okay. Now, here's where we have to be careful, because someone else could read this problem and say this. Which would mean that for them, they would get, what would they get? Let's clear that out. They would get 4 times 9 times 8. They would get 288. Choices. Now, how do you get from 3 to 4 and 8 to 9 and 7 to 8, but more importantly, why? Well, what if someone says there's a 4th choice for salads? Don't eat a salad. And there's a 9th choice for entrees. Don't order an entree. And there's a 8th choice for desserts. Don't order a dessert. Then that would be 4, 9, and 8. Now, the reason that this might not feel good for you is because it all depends on how you read that sentence right there. So what does this mean? Whoa, where'd it go? What does this mean if one of each is chosen? That says to me that you have to pick one of each. So you have to pick a salad, you have to pick an entree, and you have to pick a dessert, which is why I would argue that this is not right for this problem. Maybe in another problem we could run across one where that would make sense. All right, an apartment complex offers 1, 2, and 3 bedroom plans. They also offer each plan on either the first, second, or third floor. And if an additional option is to pay for a garage, how many different possible lease options are there at the apartment complex? Well, I'm seeing 1, 2, 3 steps. The first one is going to be bedrooms. How many bedrooms do you want? The second one is going to be the floor. You want first floor, second floor, third floor. And the fourth one is going to be the garage or not. And so the way I read the problem, there were 3 choices for bedrooms. So that would be the M1 from the formula. And there were 3 choices for the floor that you're going to live on, so that would be the M2 from the formula. And there are 2 choices for the garage, that will be the M3 for the formula, which would give us a total of 18 possible lease options. Okay. Now I think that most people are going to be okay with this because they see there's 1 bedroom, 2 bedroom, or 3 bedroom. Most people are going to be okay with this because they see that there's first floor, second floor, third floor. But where did this number come from? Well, you're either going to have a garage or you're not going to have a garage. So the 2 options there is garage or no garage. And so that's what gives us our 2 options. All right, so where does this bring us to? This brings us to a little over 11 minutes. And we're looking at, I'm gonna go here. Okay, we got time for this. Well, let's take a look at a different example. 25 entrants are in an essay contest are being considered for scholarship prizes. The scholarships are awarded to the first, second, and third place essays. In how many ways can the scholarships be awarded? All right, so this problem is actually a little different from the problems we looked at here. In each of these problems, the steps or the choices or the options, however you want to word that, they were kind of like split up. Like the bedrooms had nothing to do with the floor. You know, if I chose a 1 bedroom, it didn't have a limitation on how many floors there were or whether it could have a garage or not. Or which salad I chose didn't limit my options when it came to entrees. But down here, I can't think of this problem in the same way because if I say that M1 is to pick a first place winner, and I say that there are 25 different options for that, then M2, well, that's a different problem now because basically what's happening in this problem is we have a set and we are making subsets out of it because we're taking more than 1 choice from the same set. In these examples, we took 1 choice from this set, 1 choice from this set, 1 choice from this set. We weren't taking multiple choices from the same set. We didn't pick 2 entrees. Right? But in this one, we're taking 1 set and making multiple choices out of it. So technically, we're making subsets. Okay? To be more precise, we're making what's referred to as ordered subsets. And just as a side note, why that matters. Okay? Imagine for a second that you had a set, and we'll make it nice and simple. We'll say S is 1, 2, 3, 4. Is the set 1, 2 the same thing as the set 2, 1? Now, according to set theory, those 2 sets are the same because they are 2 sets that both have the same elements and the same number of elements in them. Now, if I asked, are they ordered subsets? Are the ordered subsets the same? We would say no, because ordered subsets require they contain the same elements in the same order. Right? That order business, the fact that ordering your subsets matters, is what makes this problem complicated. Okay. All right, so back to the problem. I have picked 1 person to be the first place winner. That is the first place winner, and there were 25 ways to do it. Now I need to pick someone to be a second place winner. I cannot pick the same person I just picked, so I only have 24 left to choose from. And so I have 24 choices. And then I need to pick a third place winner. Well, I've already picked 2 people out of the pile, so now I'm down to 23, because 24 minus 1, 23. And then the total number of ways the scholarships can be awarded is going to end up being 25 times 24 times 23. And let's see, grab my calculator. 25 times 24 times 23. 13,800. So it appears that there are 13,800 ways to give the scholarships. All right, so what we technically just did in that example is called a permutation. Okay? And this is going to give us a formula down here to simplify that process. And so the formula reads, in a set of n unique elements, so n things you can tell them apart, an ordered subset of r elements is called a permutation. Right? So the n in this formula down here, that n right there, is the number in the big set that we're pulling elements from, and that r down there is the number in the subset. So then for our example up above, we will be finding the permutation of 25P3. Now I got a formula over here, but I'm not sure what it means. So let's just take a look at it for a second. The formula says it's n factorial or n minus r factorial. Right? Are you familiar with this notation? This n factorial notation? Well, n factorial means n times n minus 1 times n minus 2 times n minus 3 times, and you just keep going until you get to 1. Like 5 factorial would be 5 times 4 times 3 times 2 times 1. 5 times 4 is 20, 3 times 2 is 6, 6 times 20 is 120. And so then 5 factorial is 120. Our example needs us to do 25P3, so that means we need to do 25 factorial divided by 25 minus 3, 22 factorial. Now that's going to be a lot of math, so I'm going to do it down here. Let's see. That's going to be 25 times 24 times 23 times 22 times 21 times 20 times 19 times 18 times, all divided by 22 factorial times 21 factorial times 20 times 19 times 18 times dot dot dot. And what you'll see is the 22, the 21, the 20, the 19, the 18, the dot dot dots, they all cancel each other. We're just left with those three out in front. So that means that our P of 25 choose 3 is going to be 25 times jeepers times 24 times 23. Calculator? Oh, I just did it. It's 13,800. So I just verified using a formula the other answer that I got. All right. Now here's the really nice thing. The good people at TI had expected that you would want to do permutations, so they built it in. It is a built-in function on your calculator. Right? The only trouble is the notation that the book uses and the notation that TI use are two different things. TI would write it like this. 25P3. And because they write it like that, that's how I have to type it in. So I'll type in 25, then I'm going to go to my math menu, over to that probability menu, option 2 NPR, and then type in the 3, so 25P3, and I get 13,800. Either way, there are 13,800 ways to, what is this? What are we doing here? Oh, yeah. To give out the money. Looks good to me. All right, I'm going to end this video here because we're not that one, this one. We're at 20 minutes, and we'll come back for more examples of permutations.